Testing, can you hear me? Testing, can you hear me? All right, my video is public now. So I'm going to be reading about trees again. So last stream I learned about binary trees. We learned about binary search trees, and we also learned about using arrays to implement complete binary trees. This stream I will start studying heaps and priority queue, Huffman coding tree. I can't remember what the Huffman coding tree is, but I guess I'll get a good revision. I just need to check a few things, and then I will start reading about heaps. All right. There are many situations, both in real life and in computing applications, where we wish to choose the next most important from a collection of people, tasks, or objects. For example, doctors in a hospital emergency room often choose to see next the most critical patient rather than the one who arrived first. And scheduling programs for execution in a multitasking operating system, at any given moment, there might be several programs, usually called jobs, ready to run. The next job selected is the one with the highest priority. Priority is indicated by a particular value associated with the job. When a collection of objects is organized by importance or priority, we call this a priority queue. A normal queue data structure will not implement a priority queue efficiently because search for the element with the highest priority will take theta n time. A list, whether sorted or not, will also require theta n time for either insertion or removal. A BST that organizes records by priority could be used with a total of n inserts and n remove operations, requiring theta n log n time in the average case. However, there is always the possibility that the BST will become unbalanced, leading to bad performance. Instead, we would like to find a data structure that is guaranteed to have good performance for this special application. This section presents the heap data structure. The term heap is sometimes used to refer to free store. A heap is defined by two properties. First, it is a complete binary tree. So heaps are nearly always implemented using the array representation for complete binary tree. Oh yeah, last stream I tried to do a complete binary tree representation using pointers, using the other representation, and the insertion was I only implemented the insert function, and it took so long. Second, the values stored in a heap are partially ordered. This means that there's a relationship between the values stored at any node and the values of its children. There are two variants of the heap depending on the definition of this relationship. So, what is fully ordered? Is like it means there's a relationship with both the parent and the children. Binary relation is called a partial order if it is anti-symmetric and transitive. The relation is also reflexive, then it is a non-strict partial order. Alternatively, if the relation is irreflexive, then it is a strict partial order. A max heap has the property that every node stores the value that is greater than or equal to the value of either of its children. Because the root has a value greater than or equal to its children, which in turn have values greater than or equal to their children, the root stores the maximum of all values in the tree. A minimum heap has the property that every node stores a value that is less than or equal to that of its children because the root has a value less than or equal to its children, which in turn have values less than or equal to their children. The root stores the minimum of all values in the tree. Note that there is no necessary relationship between the value of a node and that of its sibling in either the min heap or the max heap. For example, if it is possible that the values of for all nodes in the left subtree of the root are greater than the values for every node in the right subtree. We can contrast BSTs and heaps for the strength of their ordering relationships. BST defines a total order on its nodes in that given the positions of any two nodes in the tree, the one on the left, equivalently the one appearing earlier in the in order traversal, has a smaller key value than the one on the right. You mean for two nodes in the same depth, right? In contrast, heap implements a partial order. Given their position, we can determine the relative order for the key values of the two nodes in the heap only if one is a descendant of the other. Only if one is the descendant of the other. Okay. Min heaps and max heaps both have uses. For example, the heap sort uses the max heap, while the replacement selection algorithm used for external sorting uses a min heap. The examples in the rest of this section will use a max heap. Make sure not to confuse the logical representation of a heap with its physical implementation by means of the array-based complete binary tree. The two are not synonymous because the logical view of the heap is actually a tree structure while the physical implementation uses an array. Here is an implementation for Max heap. The class uses records that support the comparable interface to provide flexibility. We have a heap, we have a max size, we have n number of things. H heap size max, comparable H, n is the heap size, max is the inbuilt heap. So what are our, I want an example of the input. What is this heap over here? The H over here. Is it the value of the heap? It's a list of values, right? Pointed to the heap array. Heap size return n, boolean is leaf divided by 2 is less than or equal to position and position is less than n. Left child, right child, parent. So yeah, last stream I was talking about this tree structure in the array. Let this load. Yeah. So what I said, like the first is the root value, and then the next two values are the children of the root. So left child, right child. And then these two values are the children of this node over here. So left child, right child of this. And then the two after are the children of this. So left child, right child of this node over here. And it continues so on, so on. This class definition makes two concessions to the fact that an array-based implementation is used. First, heap nodes are indicated by their logical position within the heap rather than by a pointer to the node. In practice, the logical heap position corresponds to the identically numbered physical position in the array. Second, the constructor uh, takes as input a pointer to the array to be used. This approach provides the greatest flexibility for using the heap because all data values can be loaded into the array directly by the client. The advantage of this comes during the heap construction phase as explained below. Construction also takes an integer parameter indicating the initial size of the heap and and a second integer parameter indicating the maximum size allowed for the heap. But the thing is, can't we just, if the client is inputting array of values, can't we just get the size from this comparable array? Because this is Java, right? This is not C. So the client inputs this and then 99. So root, left child, right child. And then 72, 73 are children of 85. 42, 57 are children of 83. Okay. And then they add in 99 at the end. This is like physically what is in the array, and this tree is what we are imagining. So now the thing is, how do you turn this into a max heap? That's the question. So you divide this by 10 and you subtract 1 divided by 10 and floor it. So 4 times 2 is 8 plus 1 plus 2. So plus 1 is left child, plus 2 is right child. So when you add a new one, you look back to the parent and then you swap, right? You swap if the parent is smaller. This is a max heap. Yeah. And then 72 and 99 children of 85. So you compare 99 with 85 and you swap if 99 is bigger and then swap again. So we now have a valid max heap. You might expect the heap insertion process to be similar to the insert function for a BST, starting at the root and working down through the heap. However, this approach is not likely to work because the heap must maintain the shape of a complete binary tree. Equivalently, if the heap takes up the first n positions of its array prior to the call to insert, it must take up the first n plus 1 positions after. To accomplish this, insert first places v at position n of the array. Of course, v is unlikely to be in the correct position. To move v to the right place, it is compared to its parent value. If the value of v is less than or equal to the value of its parent, then it is in the correct place. And the insert routine is finished. If the value of v is greater than that of its parent, then the two elements swap position. Since the heap is a complete binary tree, the height is guaranteed to be the minimum possible. In particular, a heap containing n nodes will have a height of theta log n. Intuitively, we can see that this must be true because each level that we add will slightly more than double the number of nodes in the tree. Starting at 1, we can double only log n times to reach the value of n. To be precise, of the height of the heap with n nodes is log n floor. Each call to insert takes theta log n time in the worst case because the value being inserted can move at most the distance from the bottom of the tree to the top of the tree. Thus, to take n values into the heap, if we insert them one at a time, it will take n log n time in the worst case. Insert the stream of keys shown in the upper left corner into the original empty min heap. The heap is displayed both in the logical tree and physical array form. Clicking on, okay, let's see. So we have to click on this, right? Then 95, click on this. Clicking on an element in one will also update the other. You can insert a key by clicking an empty tree node or array cell. Once you insert a new key, be sure to update the key to restore the min heap property as necessary. So we put 22 at the end, but we need to update it since it's a min heap. So this, swap with this, and then 22 swap with 49. So the min heap is restored. Now we add 14 at the end. 14 swap with 49 and then swap with 22. 22 swap with 84. Are we allowed to have duplicate values in heaps? Because I didn't know that. 48 is bigger than 22. 21. Go back to the parent. 21, go to parent. There we have it. 13. Oh my god, 13 switches with 22. 21. And then 13 here as well. 49. 14. If all n values are available at the beginning of the building process, we can build the heap faster than just inserting the value into the heap one by one. Consider this example with two possible values to heapify an initial set of values in an array. The heap is built. The heap is built by a series of 9 exchanges in order. 4, 2, 4, 1. 9 exchanges in order. Oh, 4 switches with 2. 4 switches with 1. Is that what they say? 5, 2, 5, 4. I didn't understand what they're doing here. We can build a this heap is built by a series of 9 exchanges in the order. So 4 and 2 exchange, is that what they mean? So this turns into this. But if we start with 4, 2, 2 goes at the bottom and then 4, 1, 4 comes on top, 1 comes here. But then they're saying 2, 1. Or do I start at the end? Do I start? No, end doesn't make sense. 5, 1, 5. I think they meant 5, 1, not 5, 2. 5, 1. If 4, 4 comes here, 5 here. 6, 3, 6, 5, 3, 5. And then 7, 5, 7, 6. Yeah. 2 and 1 are in the wrong position. This heap is built by a series of 4 exchanges in order. So we start again. 5, 2, 7, 3, 7, 1, 6, 1. Because 7.17.1. Two series of exchanges to build a max heap. This heap is built by a series of 9 exchanges in the order, and then the next heap is built by 4 exchanges. It is clear that the heap for any given set of numbers is not unique, and we see that some rearrangement of the input values require fewer exchanges than others to build the heap. So, how do we pick the best rearrangement? One good algorithm stems from induction. Suppose that the left and right subtrees of the root are already heaps, and R is the name of the element that at the root. This situation is illustrated by this figure, heap 1, heap 2, R. In this case, there are two possibilities. R has a value greater than or equal to its two children. In this case, the construction is complete. R has a value less than one or both of its children. R should be exchanged with the child that has greater value. The result will be a heap, except that R might still be less than one or both of its new children. In this case, we simply continue the process of pushing down R until it reaches a level where it is greater than its children or is at the leaf node. This process is implemented by the private method shift down. This approach assumes that the subtrees are already heaps, suggesting a complete algorithm can be obtained by visiting the nodes in some order such that the children of a node are visited before the node itself. One simple way to do this is simply to work from the high index of the array to the low index. Actually, the build process need not visit the leaf. So the building algorithm can start in the middle of the array, first with the first internal node. Here is a visualization of the heap build process. Let's look at an efficient way to build a heap. We are going to make a max heap from a set of input values. So we have this, we need to build a max heap. Working from bottom to top, from right to left, do a shift down on each internal node. When they say bottom, they mean bottom, you mean from the leaves. Process node 3. When they say bottom, what do they mean by this? From bottom to top, from right to left. Process the node value 3. Since it has a smaller value than its children, swap it with the larger child. Similarly with 2. Oh, you start with the leaf and go one up, and then you arrange these two, go one up like that. So swap 2 with the larger child, swap 1 with the larger child. So I have an idea. So if we start with this, if it wasn't 7, if there was a very long subtree instead of just 7, When we bring 3 down, we bring it all the way down, right? Like as much down as we can. Your task is to reproduce the behavior of the build heap algorithm. To create a main heap from the data initially in the array, the heap is displayed in both its logical tree and physical array forms. Clicking on an element is in one will also update the other. You can swap the two record in the heap by first clicking one, then the other. Okay, so we start at the bottom. We start 58, go back up. We are making a minimum heap, right? 58, go to the parent, which is 86. 58 and 86 should swap. Go right to left. And then 86 is the biggest. Now going to 41. Between 41 and 78, 88. No, this is fine. This here is fine. Now 85. 85 is bigger than 83. No. Uh, Whoops. 85 is bigger than 83. We bring push. Oh, now what? 85 is bigger. 41. Oh, this is a minimum heap. Sorry. So 41 goes on top. We do it with a smaller child, right? Since this is a minimum. 41, 88. Push 88 all the way down. And now going from here, take the smaller child, which is 55, left to 83. 58, 41. 41, shift it up. 41 and 55, we take the smaller child, which is 41, and bring 87 all the way down. Shift it with the smaller one, right? Yeah. 87, 78. Cost of build heap. What is the cost of build heap? Clearly, it is the sum of the cost for all the costs to shift down. Each shift down operation can cost at most the number of levels it takes for the node being shifted to reach the bottom of the tree. Any complete tree, approximately half of the nodes are leaves and so cannot be moved downward at all. One quarter of the nodes are one level above the leaves, and so elements can move down at most one level. At each step up the tree, we get half the number of nodes as were at the previous level and an additional height of 1. The maximum sum of total distances that elements can go is therefore in our to log in. The summation on the right is known to have a closed form solution of approximately 2. So this algorithm takes theta and time in the worst case. This is far better than building a heap one element at a time, which would cause theta n log n in the worst case. It is also faster than theta n log n average case and theta n square worst case time required to build the BST. And let me see what this is. Let's look at a visual explanation to explain why the cost of build heap is theta n. We'll use an example with 31 records in the heap. This means there are 16 leaf nodes and 15 internal nodes. At the depth, there are to the power of 416 nodes at depth 4. These nodes are already at the bottom, so we cannot move down. At depth 3, there are 8 nodes. Each can move at most one step to reach the bottom. At depth 2, there are 2 to the power of 2 4 nodes. Each can move 2 steps to reach the bottom. And 2 nodes, each can move 3 steps to reach the bottom, and then 4 nodes. Rearrange the triangle. Hold on. So if every node goes down, if every node goes down in the worst case, yeah, it's 8, 4, 2, 1 times 2. The resulting shape is 2 to the power of 4 minus 1. Wait, what? 8, 4, 2, 1. 8, 4, 2, 1. Why did they multiply this by 2? So they rearranged 3 over here, 2 over here, 1 here. Um, 2 to the power of 4. 8, 4, 2, 1, 2 to the power of 4 minus 1. Total area of the resulting shape. Isn't it 8 plus 4 times 2 times 1 times 2 minus 1 minus 1 minus 1? Or are they doing an overestimate? You have n nodes, 31 nodes, so the total amount of work required is theta n. The total number of nodes is 1, 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 4. Theta n is the upper bound. Removing the heap or updating an object's priority. Here is the process for removing the maximum value from the max heap. We know that this value is at the root, but we also need to update the heap when we remove it. So when we do remove, we remove what? Um, we know that we want to reduce the array heap size by 1, so we swap the first and last positions. Uh, Wait, what? We know process of we know that this value is at the root. Wait, when we remove from the heap, we can only remove from the top. Can't we remove it anywhere and then adjust the heap? Where is it? Update. Where is remove? Swap update. Okay, they seem to be removing the last position. So we are switching between 60 and the last position, the root and the last position, and then we are doing the shift down thing. And then n is the heap size. N is equal to 9 instead of 10. So this value will be overwritten. Perhaps if I want to remove an arbitrary node from the heap, the client wants to do a deletion. Client that wants to do the deletion has to know the proper index for the thing to be deleted. So again, we swap it with the last position and then we update the heap. Is that what we do? Yeah. The heap is a natural implementation for the priority queue discussed at the beginning of this section. Jobs can be added to the heap when needed. Method remove max can be called whenever a new job is to be executed. Some applications of priority queues require the ability to change the priority of an object already stored in the queue. This might require that the object's position in the heap representation be updated. Unfortunately, a max heap is not efficient when searching for an arbitrary value. It's only good for finding the maximum value. However, if we already know the index for an object within the heap, it is a simple matter to update its priority or remove it. The remove method takes as input the position of the node to be removed from the heap. A typical implementation for the priority queue requiring updating of priority will need to use an auxiliary data structure that supports efficient search for objects such as BSD. Records in the auxiliary data structure will store objects heap index so that the object's priority can be updated. Priority queues can be helpful for solving graph problems such as single source shortest paths and a minimal cost spanning tree. Okay, I thought they would go more in depth with the priority queue. So when implementing a priority queue, these values will have additional data about what job they're referring to, right? Consider a node R of a complete binary tree whose value is stored in position I of an array representation for the tree. If R has a left child with the child's position, if R has a left child, where will the left child's position be in the array? I. So if it's I, then the left child is I times 2. 0, 1, 2, 3, 4, 5, 6, 7, 8. I times 2 plus 1. What is the position in a maxi? What is the position of the element with the greatest value? 0. Consider a node R of a complete binary tree whose value is stored in position I of the array representation for the tree. If R has a left child, where will the... Okay, this is the same question. One can often gain an improvement in space requirements in exchange for a penalty in running time. There may be situations where this is a desirable trade off. A typical example is storing files on disk. If the files are not actively used, the owner might wish to compress them to save space. Later, they can be uncompressed for use, which costs some time, but only once. You often represent a set of items in a computer program by assigning a unique code to each item. For example, the ASCII encoding scheme assigns a unique 8-bit value to each character. It takes a certain number of bits to provide enough unique code so that we have a different one for each character. For example, it takes log 128 or 7 bits to provide 128 unique codes needed to represent the 128 symbols of the ASCII character set. The requirement for log and bit to represent any unique code values assume that all codes will have the same length as our ASCII codes. These are called fixed length codes. If all characters were used equally often, then a fixed length coding scheme is more space efficient method. However, you're probably aware that not all characters are used equally often in many applications. For example, in various letters in an English language document, the various letters in an English language document have greatly different frequencies of use. So A has the highest frequency. So in 1000 letters, A has the highest frequency, B second. No, E has the highest frequency. Where is it? E has the highest frequency. Some characters are used more frequently than others. It is possible to take advantage of this fact and somehow assign them shorter quotes. The price could be that other characters require longer quotes, but this might be worthwhile if such characters appear rarely enough. This concept is at the heart of file compression techniques in common use today. The next section presents one such approach to assigning variable length codes called Huffman coding. While it is not commonly used in its simplest form for file compression, Huffman coding gives the flavor of for such coding schemes. One motivation to study Huffman coding is because it provides our first opportunity to see a type of tree structure referred to as a search tree. How do you pronounce this? Search tree. You just pronounce it as tree. Huffman coding assigns codes to characters such as the length of the code depends on the frequency, relative, or weight of the corresponding character. Thus, it is a variable length code if the estimated frequencies for letters match the actual frequency found in an encoding message, then the length of that message would typically be less than if a fixed length code had been used. The Huffman code for each letter is derived from a full binary tree called the Huffman coding tree, or simply the Huffman tree. Each leaf of the Huffman tree corresponds to a letter, and we define the weight of the leaf node to be the weight of its associated letter. Code is to build a tree with the minimum external path weight. Define the weighted path length of a lead to be its weight times its depth. Binary tree with the minimum external path weight is the one with the minimum sum of weighted path lengths for a given set of leaves. A letter with high weight should have low depth so that it will count the least against the total path length. As a result, another letter might be pushed deeper in the tree if it has less weight. The process of building the Huffman tree for n letters is quite simple. First, create a collection of n initial Huffman trees, each of which is a single leaf node containing one of the letters. Put the n partial trees onto a priority queue organized by weight, frequency. Next, remove the first two trees, the ones with the lowest weight, from the priority queue. Join these two trees together to create a new tree whose root has the two trees as children and whose weight is the sum of the weights of the two trees. Put this new tree back into the priority queue. This process is repeated until all the partial half entries have been combined into one. The relative frequencies for 8 selected letters. The following slideshow illustrates the Hartman tree construction process for the 8 letters of table 7.18.2. Wait. Following letters C, D, E, K. Okay. Sorting data by frequency results in the following. Okay. Choose the two smallest. Merge them together to form a tree with some 9. Reorder the list. Merge them together to form a tree with some 33 and reorder the list. Wait. I don't get how this is being done. Merge them together with to form a tree with some 65 and reorder the list. Choose the two smallest, 37 and 42. Merge them together, form a tree with some 79. Reorder the list. Choose the two smallest. I don't get how this is done. Huffman coding assigns codes to characters such that the length of the code depends on the relative frequency or weight of the corresponding character. Thus, it is a variable length code. If the estimated frequency for letters match the actual frequency found in the encoded message, then the length of that message will typically be less than if a frequency code had been used. Fixed length code had been used. The Huffman code for each letter is derived from a full binary tree called the Huffman coding tree or simply the Huffman tree. Each leaf of the Huffman tree corresponds to a letter, and we define the weight of the leaf node to be the weight of its associated letter. And let me see again. So order them by relative frequency. Add the smallest two, put them in the tree 9, 24, 9. So 24 gets added with 9, makes 33. Choose the two smallest number. Hold on. So before, okay, so this 9 here is part of the list. So 9 and 24 combined, these are the two smallest, so we put them together. Okay, so 33 and 32 are the smallest, we put them together. 65, 42, 42, 73, 73 and 42 are the smallest, we put them together. 42, 65, 79, 120. So 42 and 65 are the smallest, we put them together. And 107 and 79, they are the smallest, we put them together. So they become siblings, and then E and 186 become siblings. I see, I see. This implementation is similar to a typical cross hierarchy for implementing full binary trees. It is an abstract base class called named half node and two subclasses named leaf node and int l node. What is int l node? Oh, internal node. This implementation reflects the fact that the leaf and internal nodes can contain distinctly different information. Here is the implementation for the Huffman tree class. Uh, Here is the implementation for the tree building process. Okay, build half takes as input FL, the minimum heap of partial Huffman trees, which initially are single leaf nodes, are shown in step 1 of the slideshow above. Body of the function build tree consists mainly of a for loop. On each iteration of the for loop, the first two partial trees are taken off the heap and placed in variable temp 1 and temp 2. Is created temp 3 such that the left and right subtrees are temp 1 and temp 2 respectively. Finally, temp 3 is returned to FL. Fn is the full tree, right? And where is FL? ASCII coding actually uses 8 bits per character. 7 bits are used to represent 128 codes of the ASCII character set. The 8 bit as a parity bit that can be used to check if there is a transmission error for the character. Assigning and using Huffman codes. Once the Huffman tree has been constructed, it is an easy matter to assign codes to individual letters. Beginning at the root, we assign either a 0 or a 1 at each to each edge in the tree. 0 is assigned to edges connecting a node with its left child and 1 to edges connecting a node with its right child. This process is illustrated in the following slideshow. So 0, 1. So 0 to the left, 1 to the right. 0, 1, 1, 1. Now we see how to assign. Now we see how the edges associate with bits in the code. There's a simple method to generate the codes for each letter. Here is the Huffman coding tree we are using. Now we are ready to compute. CS1110. 0, K is this, L is this, M is this. Note that we have a code for each length. Encoding a text message. Coding a text message is done by replacing each letter of the message with its binary code. A lookup table can be used for this purpose. A set of codes is said to meet the prefix property if no code in the set is the prefix of another. The prefix property guarantees that there will be no ambiguity in how a string is decoded. In other words, once we reach the last bit of a code during the decoding process, we know which letter it is the code for. Huffman codes certainly have the prefix property because any prefix for a code would correspond to an internal node, while all codes correspond to leaf nodes. When we decode a character using the Huffman coding tree, we follow a path through the tree dictated by the bits in the code string. Each 0 indicates left and 1 indicates right. The word deed is represented by 101000101. So 101. 101 is D. 0 is E. 0 again is E. 101. 101. For the Huffman tree shown below, what is the corresponding sequence of bits represented by E? Type its representation as a series of ones and zeros. So E is just 1, 1. Now they want 1, 0, 0, 1, 0, 1. J. 1, 0, 0, 1, 0, 1. Oh, do I have to write capital J? 1, 0, 0, 1, 1, which is capital V. ET 1, 1, 0, 1. 0, 0. 0, 0, 1, 0, 0, 1, 1. In theory, Huffman coding is an optimal coding method whenever the true frequencies are known and the frequencies of a letter is independent of the context of that letter in the message. In practice, the frequencies of letters in an English text document do change depending on the context. For example, while E is the most commonly used letter of the alphabet in English documents, T is more common as the first letter of a word. This is why most commercial compressions utilities do not use Huffman coding as their primary coding method, but instead use techniques that take advantage of the context for the letters. Another factor that affects the compression efficiency of the Huffman coding is the relative frequencies of the letters. Some frequency patterns which save no space as compared to fixed length codes. Others can result in great compression. In general, Huffman coding does better when there is large variation in the frequencies of the letters. In a particular case of the frequency shown in table 7.18.1, we can determine the expected savings from Huffman coding if the actual frequencies of the coded message match the expected frequencies. Because the sum of the frequencies is 306 and E has a frequency of 120. So which table is this? E is 120. Expect it to appear 120 times in a message containing 306 letters. The actual message might or might not meet this expectation. Letters T, L, U have code lengths of 3 and together are expected to appear 121 times in the 306 letters. Letter C has a code length of 4 and is expected to appear 32 times in 306 letters. The average expected cost per character is simply the sum of the cost for each character times the probability of it occurring, or C1 P1, C2 plus C2 PT, P2. This can be recognized as C1 F1 plus C2 F2 plus all the way to Cn Fn, where Fi is the relative frequency of letter R and Ft is the total for all letter frequencies. We see that all letters with codes beginning with 0 are stored in the left branch, while all letters with code beginning with 1 are stored in the right branch. Contrast this with storing records in ABSD. There, all records with key value less than the root value are stored in the left branch, while all records with key values greater than the root are stored in the right branch. Recall that the Huffman coding tree stored in the left branch. Stored in the left branch. All letters. What? Recall that the Huffman coding tree. Should it be stores? Stores in the left branch. All letters whose codes start with 0. Then the right branch. Oh, stored. Yeah, yeah. Huffman coding tree stored in the left branch. All letters whose codes start with 0. And in the right branch, all letters whose codes start with 1. You can use the same concept to store records in the search tree. This is that is slightly different from the behavior of a BSD. We can view all keys stored as appearing on a number line. BSD splits the number line based on the position of the key values as it receives them. In contrast, we could split key values based on their binary representation, similar to what Huffman coding tree does. The following slide shows present this in more detail. 12, 30, and they added 55, 59. I want to search up the exact definition. Uh, a form of search tree where an internal node represents a split in the key space at a predetermined location rather than a split on the actual key values seen. Example, a simple binary search tree for given values in the range of 0 to 1023 would store all the records with key values less than 512 on the left side and all the records with key values equal to or greater than 512 on the right side. Tree is always a full tree. Folklore has it that the term comes from retrieval and should be pronounced try, in contrast to tree. Try is sometimes used as a synonym for the alphabet try. So 0 children or 2 children. Demonstrate the characteristics of a try. We will display this on a number line. We'll start with an empty try. First we had 38, no splits required. Now we now add 19. A single split is required to split the timeline in half at the value of 32. So 19 and 38. Now we add 7. This requires a single split at value 16. But how does it decide this 19 over here? 36. For first insert 36. Number line is split at 36. So the number line is from 0 to 70. 18, 9. This is a normal tree. This is not a try, right? 18 is added 9, 43, 50, 63. More than, less than. Hold on. Less than, more than, less than. Okay. That's how we got 23. But how did we get this 38 over here? 32, 38 is first added. On that I understand. 38, 0, 64. When it adds 19, hold on, 38. When it adds 19, the split is the middle value between 19 and 38. No, not the middle value. Shouldn't 32 be closer to 19? Anyways, single split is required to split the timeline in half at value 32. Oh, the entire timeline is 0, 64. So splitting it in half gives 32. These are the two values we inserted. What is the next value we insert? So we added 7. We added 7. Now the new split is at 16. So the internal nodes represent a middle split. So cut it by half, 32. Between 32 and 0, cut it by half, 16. The next value is 48. Wait. Next value is 48, right? So 32 plus 64 divided by 2. 32 plus 16 is 48. No, the next value is added as something else. And the split is at 48. But what if it was 48 itself? So they made a split between 32 and 48, and then another split between. So they made a split between 32 and 64, 48, and then another split between 32 and 48, which gives 40. All right, all right. Wait. Hold on. Um, so they did this. Just until here. If I didn't add 50, what would have happened? 38. Now we add 40. This requires 45. This requires two splits. First at, and now we try adding 45 again. Yeah. But if I didn't add 50, what would happen? Huffman tree building is an example of a greedy algorithm. At each step, the algorithm makes a greedy decision to merge the two subtrees with the least weight. This makes the algorithm simple, but does it give the desired result? This section concludes with the proof that the Huffman tree indeed gives the most efficient arrangement for the set of letters. The proof requires the following lemma. For any Huffman tree built by the function build-huff containing at least two letters, the two letters with least frequency are stored in sibling nodes whose depth is at least as steep as the other leaves or the leaf nodes in the tree. Call the two letters with least frequency L1, L2. L1, L2. They must be sibling because build-huff selects them in the first step of the construction process. Assume that L1 and L2 are not the deepest nodes in the tree. In this case, the Huffman tree must either look as shown in figure 7.20.1 or effectively symmetrical to this. For this situation to occur, the parent of L1 and L2 labeled V must have a greater weight than the node labeled X. Otherwise, the function build-huff would have selected V in place of node X as the child of U. However, this is impossible because L1 and L2 are letters with the least frequency. Function build-huff builds a Huffman tree with minimum external path weight for a given set of letters. Okay, I will. For n is equal to 2, the Huffman tree must have minimum external path weight because there are only two possible trees, each with identical weighted path nets for two leaves. Assume that any tree created by Bill Huff that contains n minus 1 leaves must have minimum external path length. Given a Huffman tree built by Huffman with n leaves, n is greater than or equal to 2. Suppose W1 is less than W2 is less than Wn, where W1 to Wn are the weights of the letters. Call V the parent of the letter with frequencies W1 and W2. From the lemma, we know that the leaf nodes containing the letters with the frequency V1 and V2 are as deep as any nodes in T. If any other leaf nodes in the tree were deeper, we could reduce their weighted path length by swapping them with W1 and W2. But the lemma tells us that no such deeper nodes exist. Call T apostrophe the Huffman tree. It is identical to T except node V is replaced with a leaf node V apostrophe whose weight is W1 plus W2. By the induction hypothesis, T apostrophe has the minimum external path length, returning the children to V apostrophe restores tree T, which must also have minimum external path length. Yeah, I understood nothing. Anyways, next chapter. Then just this summary. The next chapter talks about sorting. Okay, I will end the stream here then. And yeah, then I will see you guys whenever. Bye.